Thank you for coming. My name is Karl Karlstrom, and with my wife, Laura Crossley, who talked about another site within a site, the Great Unconformity. We've been working there for 3 or 4 decades, and Grand Canyon is already a UNESCO World Heritage Site, and I think the park officials were a little puzzled about the geoheritage thing. Why do we need to be a geoheritage site? We're already a UNESCO World Heritage Site. I didn't know what to answer, but now I do. After this meeting, I can see that we collectively have a role to play. It's probably different in each geoheritage site, but we have a role to play to kind of push on the administrators and the managers to emphasize the geologic aspects, the science literacy aspects of these special places. So that's I've gained a lot from this meeting. I thank the conveners for that, and I have sort of new resolve to continue to work with the park. It's in the geomorphology section, but it could be in so many sections. It was in the stratigraphy section yesterday. It could be in the tectonic session. I'm a tectonicist myself, and I'm interested in all ages of tectonism. And so this idea that this canyon, which is so famous around the world, is a geomorphological feature is important. And in fact, but it sort of hides this deeper geologic 2 billion years of rock that you can use for research and education. We do a lot with public education. There's 6 million people a year that come to Grand Canyon, and we've helped with exhibits and this sort of thing. And it's really quite amazing, the range of knowledge. We see a lot of people come and they know a lot of geology and they're learning more. We see people who are so challenged with time, as we all are challenged with the concept of time, but one of the fundamental messages for the visitors at Grand Canyon is that it's a young canyon, and it's carved into very old rocks. And they get mixed up about the rocks that are exposed in the walls of the canyon versus the actual geomorphology. Does anybody know the age of the Grand Canyon? Yes. What is it? Throw some numbers out. Yes, okay, so the age of the Grand Canyon has been debated for 150 years since John Wesley Powell. The park is 100 years old. We've been working with the park on a number of sort of projects to highlight this history. For those of you who haven't been there, please go. It's your first opportunity. It's on the edge of the Colorado Plateau, and it's a gash. It's a canyon carved through an uplifting plateau in a very strange zigzag pattern. It comes south and goes west and south, and that pattern itself is a clue to the age of the canyon. There's not just one age. It's a canyon which has linked together older paleo canyons when it finally got integrated in its modern path. It's the single river that drains the western side of the Rocky Mountains, the yellow line there. And it's the only river system that takes water off of the Colorado Plateau. And again, is that an old feature or a young feature? Geomorphologically, the answer is yes. There's old landscape features embedded in a overall young landscape. In a perspective view, you can see the tributaries of the Colorado River system coming from the Rockies, the different, the Little Colorado River down here, the San Juan River, the Green River, and here's Grand Canyon, and here's this zigzaggy pattern. It comes south, and then it cuts across an uplift. What a dumb river. Why would a river go across an uplift? That's what puzzled John Wesley Powell, and still has puzzled a lot of people. Then it turns west, and it goes south along this fault zone. So it's actually pieced together from a number of different segments as the river became integrated from top to bottom. And we've been dating paleo river deposits and terraces, trying to figure out how fast it's carving. Everybody knows how fast it's carving. It's about the thickness, on average, the thickness of a piece of paper every year will carve the Grand Canyon in 5 or 6 million years. That time element that's so important, thickness of a piece of paper is small, 5 million years or 6 million years is long, so you can carve a 1.6 kilometer deep canyon in that time. But again, this river, which is carving through this landscape, is exposing a whole wealth of other geologic problems besides geomorphic ones. And so you get good after a while at turning the little switch in your brain. I'm no longer thinking about the landscapes in the basement rocks. I'm thinking about how the continent was put together by collision of volcanic arcs, and what it must be like in the middle crust, 20 kilometers deep, beneath high peaks of what we call the Vishnu Mountains for these basement schists and gneisses and plutons, which represent the first cycle formation of continental lithosphere. So that was my initial interest in Grand Canyon. In the 1980s, I didn't care about the geomorphology, I didn't care about any of the overlying sedimentary rocks, and we were working on developing the pressure, time, temperature, deformation history of these rocks. They were sedimentary rocks. They started at the surface, buried by thrusts and folds to deep levels, 20 kilometers, 25 kilometers deep, and now they're back at the surface. What a wonderful journey these metamorphic rocks have taken that they can tell us about if we understand their evolution in time, temperature, space, pressure space. Then this tilted set of rocks, we call it the Grand Canyon Supergroup, and Laurie talked about those yesterday. They record an entirely different story. We're inside of the continent of Laurentia, and these sedimentary rocks are recording things around the edges, plate tectonics around the edges, when the supercontinent of Rodinia was being assembled to deposit these rocks and broken apart to deposit those rocks. So they're telling us about things at the edges of the plate. And then these basalts are evidence of a plume that came in 1.1 billion years ago. So we spent the 90s really working on this Grand Canyon supergroup. Here's the great unconformity that's really multiple unconformities, as Laurie talked about. And then the Paleozoic flat-lying strata, which some visitors go there and they don't even really see down into the basement rocks. But there we have the record of the evolution of life on Earth in the Paleozoic. It's a spectacular section, not complete, as no sections are, but where it is exposed, it's fantastic. So just a comment or two about each of these research topics, which have been occupying us for decades. This is Sam Bowring from MIT. He's passed away now, but this was the first attempt in the 80s to put really precise uranium-lead zircon ages on the basement rocks and understand their pressure, temperature, and time history. So that was a good effort. In fact, we're starting again that process with Sam's student, or past student, Mark Schmitz, to try and get ever more precise ages as we have better technologies. This is in the Chuar group in the tilted section, and a colleague of ours, Susanna Porter and Karl Daler, call these things the first vampires. The first vampires. These are the first predators, the first heterotrophic organisms on Earth, 750 million years ago. You can see the little holes. These are about about a tenth of a millimeter, tiny, tiny things called vase-shaped microfossils. You see the holes where one of them was eating into another. And then you start down these paths. I never thought I would work on the Paleozoic rocks, but we were working on dating these tilted rocks for about 10 years with detrital zircons, and we never could get young grains to get the bottom bracket, a maximum depositional age. We finally did, and we found out, to my chagrin, that these are Cambrian underneath the unconformity. So we have a whole interesting new twist now. These are lower Cambrian, these are middle Cambrian, and we've started to redefine the Cambrian timescale, again with detrital zircon geochronology on the sandstones. Oh, I should mention the trilobites. The trilobites, the Cambrian now starts at 539. The IUGS chart will say that soon, I believe. And the middle or lower to middle Cambrian boundary is now at about 505. It says 509 on the chart, but that'll, the knowledge we gain is going to gradually work its way into the standardized stratigraphic charts. But the trilobites are radiating and going extinct at an amazing rate. These biozones last less than 1 million years. So all of this Cambrian diversification of life, the explosion of life, if you will, is getting shorter and shorter in time. Very interesting thing. And the global implications of, in this case, the Olanellids are blue and the Paradoxides are green. They were thought to go extinct at the same time, but now we know slightly different times because of the precise geochronology. Okay, back to geomorphology. John Wesley Powell noted as he floated down the river that there were lava flows that poured over the sides of the canyon and dammed the river. And he has a wonderful quote, "What a conflict of water and fire there must have been here. Imagine a river of molten rock running down into a river of melted snow." He was quite a poet. His prose was excellent. "What a seething and boiling of waters, what clouds of steam rolled into the heaven." Powell was inspirational for early scientists. He was one of the early U.S. Geological Survey founders, and we now know from dating and correlating these lava flows, there were 17 times at least when the basalts dammed up the river. The river makes short work of these dams, as it will of the modern dams. There's lessons that geology teaches us developers. And so the implications of what we do in this case, they lasted 10,000 years, something like that. It's hard to estimate exactly, but present dams are filling with silt very quickly. They will overtop with water, cut back through, and the river will establish itself past the dams again. That will be a new geoheritage site when the dams are broken down by the river. This is John Wesley Powell. He's a major in the Civil War. He got together a motley crew of mountain men and ex-soldiers, and for the first time found the path of the Colorado River through the Grand Canyon. But he was very interested in ethnology as well, and we work a lot now with the 11 affiliated tribes that live all around the Grand Canyon and want to have more of a voice in the preservation and management of the region. Their message to us all, as our colonialists, is we're still here. And then the scientific legacy of this place is really hard. Geology is developing in Europe and in the US in the late 1800s in parallel. And from a geomorphology point of view, the western US landscapes, which were so well depicted here by William Henry Holmes, these were lithographs. He scratched these little scratches in limestone, put the ink on, put the paper on the ink. They're just marvelous pieces of art. And that's really not an exaggeration. That's what the Grand Canyon looks like from Toroidal Point. Here's Dutton's map through Grand Canyon, showing the Grand Staircase. When you go to Grand Canyon, go up to Zion and see the Grand Staircase and these volcanic fields around. Really excellent map for the late 1800s. So in 1995, we were doing research there, and we said, the park is doing a terrible job of trying to, their resource, in our opinion, is geology. They think about the condors and the squirrels, and those are resources too. But the geology is their heritage, so we keep pushing them. How can you transmit knowledge about the Earth to 6 million people a year? We propose to them a walking trail of time, we call it. It's as you walk along the rim, it's handicapped accessible. Each step you take, each long step, each meter, is 1 million years of time. So to walk from today, which is here, by the museum, the Yavpai Geology Museum. To walk from today to the age of the Earth is 4.5 kilometers. It's a decent walk. It's so gorgeous on the rim, and along the way, you'll find rocks of all the ages, from all the layers, and people really like it. And we hear geology discussed in every language on Earth, which is very gratifying. We've been running a series of research trips. After decades of work, we're saying, how can we A, pull together the back burner of all the work we haven't published yet, and B, invigorate a new generation of geology research and researchers. And so we've been running these river trips it takes 11 days. We have different topics. This was the last one we ran. It was on springs and groundwater and travertine. And I think of Grand Canyon as a geomorphic feature or as a way to look at these different chapters of Earth history. Another way to look at the Grand Canyon is as an incised aquifer. We see the springs, we see the water, we see the aquitards, and we can understand pathways that water takes. And that's a gold mine of information for an arid region that's being overused, overdeveloped. So these beautiful springs are carbonic. They have CO2 from mantle gases, and we've done noble gas work on them. Anyway, it's a whole new story about how to manage springs and groundwater that we're trying to get the park to pay more attention to in cooperation with the tribes. So our emblem, rock captures time, time carves a canyon, and canyon reveals rock, expresses sort of a cyclical rock cycle approach to understanding geology. Thank you.